Ionization energy is the amount of energy required to remove an electron. It's typically measured from an atom or ion in the gaseous state. So don't be freaked out if you see little equations, kind of like this aluminum equation in the center. This would represent ionization energy if I wanted to write an equation for it, where I would have the gaseous atom and I'm removing an electron to form a positive ion. And again, it's not typical that we would see aluminum in the gas phase, but ionization energy is measured for that atom or ion in the gas phase. Now you might notice this, when we look at ionization energies, they will be positive values because they are endothermic. It's energy that must be added to remove an electron. And again, think about it in this way, that I've got the positive nucleus and the negative electrons. Opposites attract. Yeah, I mean, some atoms really want to lose electrons, but you're still going to have to add a little bit of energy to remove that electron from the attraction of the positive nucleus. So they'll always be reported as positive endothermic values, usually in units of kilojoules per mole. And the other thing that you might notice is this little subscript 1 or 2. The 1 would refer to the first ionization energy. That would be the energy required to remove the first electron, or in other words, like the highest energy electron, the one that's furthest from the nucleus, or the one that's got the least attraction to the nucleus. That's always the one you're going to lose first. The second ionization energy would be to remove like the next electron, the one that's got the second lowest, attraction to the nucleus, and so on. So here's kind of a good example that you could have, the aluminum atom. If I remove the first electron, we call it the first ionization energy. I would have to add 580 kilojoules per mole. Now look what happens to the second electron. Now what if I have the aluminum plus 1 ion, and I want to remove one more electron? I want to form an aluminum plus 2 ion. Notice that the ionization energy increases. That's something that they're going to ask you to rationalize. Why is the second ionization energy greater than the first? And we're going to say, oh gosh, piece of cake, I'm going to nail this. Think about what we're dealing with. The aluminum atom. Aluminum is element number 13. So there are 13 protons and 13 electrons, and we really don't care about the neutrons. Okay, so there's attraction there. That's a good thing. So here's the aluminum atom. Now let's look at the aluminum plus 1 ion. There are still 13 protons, but you've lost an electron, so now there's only 12. Oh, guess what? The nucleus is the same, but in this plus 1 ion, we've got less electrons. Well, with less electrons, there's like more of a pull coming from that nucleus. It's like the positive nucleus is attracting less electrons, so that attraction per 12 electrons, per each of the 12 electrons, is stronger. So with fewer electrons, the nucleus will have a stronger pull on the existing electrons. So as you keep trying to remove electrons, if I were to go now to the third ionization energy, what if I want to remove the third electron from aluminum? Each time you remove an electron, ionization energy increases. And they're going to ask you why. And you'll say, piece of cake. Same amount of protons, but less electrons. So there's more of a pull, there's a greater attraction for those 12 electrons than there would be 13 electrons. Think about everything in terms of like what's comprising the atom. Break it down into a balance between protons and electrons. Now this chart's really interesting. Take a peek at this. Let's look at aluminum. Okay, so we've got the first electron, the second electron. We kind of mentioned those two. aluminum. Removing the first electron, I have to add 580 kilojoules of energy. Going to the second electron, it increases. Going to the third electron, it increases even more, which is what I expect. There's going to be 13 protons, but less electrons. So there's a stronger attraction for the existing electrons. But now look what happens as I go from the third electron to the fourth. Holy buckets. You know, they increase in a relatively steady increment, but then all of a sudden I go from like almost 3,000 kilojoules per mole to like 11,000 kilojoules per mole. Holy man, that's a pretty substantial increase in ionization energy. So this would be another thing they would ask. Okay, number one, part A. Why does ionization energy increase for each successive electron removed? And we talk about the attraction between the nucleus and the existing electrons. Part B. Why is there such an increase, such a dramatic increase, removing 3 electrons to removing 4? Now think about the structure of an aluminum atom. So aluminum atom, number 13. I'm going to do this the long way because it's not that big of an atom. 1s2, 2s2, 2p6, 3s2, 3p1. Alright, so we're going to split these electrons into 2 groups. We've mentioned the term valence electron. Valence electrons are all the electrons in the highest energy level. Now here's a rookie mistake. People will look at this configuration and they'll be asked how many valence electrons? They'll say 1. They'll say there's 1 electron in that 3p orbital. The valence electrons are all the electrons in the highest energy level. The highest energy level is the 3rd. So the valence electrons are all the electrons in the 3rd energy level. So it's the S's, the P's, all that good stuff. Well, yeah, I mean, if we look at the periodic trend, we know that aluminum should have 3 valence electrons. The rest of these guys, the electrons in the 1st and 2nd energy level, these are your core electrons. So really, when we talk about bonding, the core electrons are not involved in bonding. So in the next chapter, we're only going to look at the valence electrons. The core electrons are all in stable, filled orbitals. They're pretty boring. It's the valence electrons that make things a little spicy. Okay, so think about this. We'd said, okay, you got to remove the first electron. That's fine. It's in a p orbital. You know, it's a little higher energy orbital. It'll be pretty easy to lose that first p electron. And then I've got these 2 s electrons, and yeah, I still want to lose them. Yes, it's going to take a little more energy to remove the second p electron, because again, there's still the same amount of protons, so there's a greater attraction for these existing electrons. But in general, aluminum would like to remove those valence electrons. Then he's down to a stable ion where all the energy levels in the orbitals are filled. Well, not all the energy levels, the existing energy levels are filled. But what if you remove the 4th electron? So removing these guys, this is fine. We would like to remove those. But do we want to remove the 4th electron? That would mean that we're removing one of these 2p electrons. Wow, I don't want to do that. The aluminum plus 3 ion is stable. 2p6, that's stable. All the orbitals are filled. The second energy level is full. I don't want to lose a 4th electron. You never want to lose core electrons. The core electrons are stable and paired. So you'll notice this huge jump in ionization energy when you move from valence electrons to core electrons. So all of these would be considered valence electrons. So for example, like sodium. Sodium would like to remove one electron, but does sodium want to remove two? No! Going from the first ionization energy to the second, it goes up like tenfold. No, I don't want to remove a core electron. Sodium only wants to remove one electron. Now the most stable magnesium ion is +2. Yeah, we want to lose 2 electrons, but we don't want to lose 3. So every time you see this big gap, this big jump in ionization energies, you're always moving from valence electrons to core electrons. We don't want to remove the core electrons. They're stable and paired.